Hello everybody, and welcome to our third keynote session of the 16th OpenFOAM Workshop. This keynote, I'm delighted to welcome Professor Deborah Greaves from the University of Plymouth in the scenic southwest of England. So I had the pleasure of attending the CCPI WSI Code Developers Workshop earlier in the year, and I was struck by the breadth of different modeling techniques that were used at the workshop. So I'm looking forward to seeing Professor Greaves' keynote today. So Professor Greaves, feel free to turn on your camera and share your screen when you're ready. So if people have questions, please put them in the Q&A and we will have time at the end to ask them. Thanks very much.
Okay, thank you very much indeed, Philip. I hope you can see my screen all right, can you?
Yep, yeah, perfect.
Okay, that's brilliant. All right, well, thank you very much for the introduction and good afternoon, everybody. Thank you very much indeed for the invitation to come and talk to you today about the collaborative computational project on wave structure interaction, the CCP-WSI. I'm very grateful for the opportunity. As Philip says, I'm Deborah Greaves. I'm Professor of Ocean Engineering at the University of Plymouth. And I'm leading this CCP-WSI. What I'd like to do today is just run through an introduction to the CCP, talk a little bit about some of the applications we're interested in working on, some of the coupling and parallelization work we're doing, the blind test series that we've been running, and also some of the opportunities to engage with us and get involved in some of our events. So first of all, I'd like to introduce the team. Here we all are. It's a collaboration between the University of Plymouth, Manchester Metropolitan University, City University London, University of Bath, Exeter, Manchester, Newcastle University, the University of Glasgow, and also STFC. So within this team, we have a number of people with expertise in developing numerical models and applying them and computational fluid dynamics using a range of different techniques. And the key thing that we're trying to do in this CCP is to help to develop the code, the community code for wave structure interaction. And that means coupling together the computational fluid dynamics part with the structural dynamics. And the CCP program is a research funding program which is run through the EPSRC, and which is the Engineering and Physical Sciences Research Council. And these CCPs tend to run on a sort of 5-year program. We had a CCP WSI that ran from 2015 to 2020, and we've just had the renewal for 2020 to 2025. And in this new phase, we're bringing in some more expertise on the computational structural mechanics side in order to strengthen that aspect of the team. We have a wide network. So the team members you've just seen are sort of responsible for delivering the networking activities and running the CCP. But we work with a very large number of partners and others within the wider network. And the wider network includes universities and industry. These logos are the network members who supported our bid, our proposal for this. But of course, the network is also much wider than that. And if you're not already involved, we'd like to invite you to join our network. And it's very easy to do that through the website link, which I shall put up a bit later on. So as I said, this is a CCP in wave structure interaction. So we're really looking at coastal or marine or ocean engineering type applications. But we want to include the wave element, the water wave, and also the structure. So the wave structure interaction, the hydrodynamics, and also the structural response and structural mechanics, rigid body motion, and also the elastic response. And the aim of the CCP is to develop and maintain the robust and efficient computational WSI modeling tool, and that modeling tool can be a combination of a number of different types of numerical model. And the reason for that is that if we look at the diagram there, you can see there's a monopile from a floating offshore wind structure, potentially with a wave impacting it. And there are some boxes around those different regions, and that represents different domains around the structure and the waves. And in each of those different domains, you may need to take a different numerical approach in order to realize and simulate the different physics within there. So, for example, if we look at the wave generation area away from the structure, then a fully nonlinear potential flow theory solution might be good. But if we can move to an incompressible Navier-Stokes solver closer to the structure, we'll perhaps be able to pick up more of the detail of the free surface and how that moves around. And then in the very local area close to where the wave is interacting with the structure, if the wave's breaking or if it's entrapping air in its interaction with the structure, it might be important to include compressibility in there as well. And that's really just thinking about the fluid side. If we include thinking about the structure as well, then we want to make sure that we've got the right sort of computational tool for the structural part. And then we need to think about how those different computational tools will talk to one another and couple together in the right way. So we're interested in a number of different modeling tools and how we can build those together in order to solve some of the very complex wave structure interaction problems that we need to investigate now. So within this project, we have a number of a series of networking activities to help build the community and to provide a focus for software development, bringing developers and HEI academics together with industry, so developers together with users as well. Here's the website address, but that'll appear many times during the talk, so hopefully you can find it easily. So our objectives are to bring together computational fluid dynamics with the computational solid mechanics communities, providing training and workshops and focus around benchmark tests and blind test series and activities and working together to move the codes further on, to support the codes we have, to develop new ones and move them further on as needed to suit the applications we need to look at. How do we do that? Well, we run a number of networking activities, and here are some photographs from some of those that have happened over the last few years. I'm sure some of you are in these pictures, but we run training events. So we have a repository for the code, and we have some training events around how to use that, and also how to develop codes and how to software engineering and good practice. We also have workshops for code developers, and this is where we bring people together to share their developments and in a sort of conference type structure. And we had one recently, as Philip mentioned, in April, where we brought together a number of different people using different codes. So we do those periodically. We also run hackathons, which is more of a focused event over a number of days, a few days. It tends to be a residential event where people come together with a bit of pre-planning and ideas around what they'd like to do within the workshop, within the hackathon, and then work together in order to make some advances in the software. And then there'll be some experts there as well on hand to help. The focus group workshops are workshops that we run together with academics and with industry, and the point of those is to help us to develop a sort of priority list of challenges or a roadmap to think about what are the types of applications we're going to need to solve in the future, and what are the sort of roadblocks to those happening, what innovations and what research needs to be targeted in order to develop the codes so that they're fit for what we need them to do. And then we also set up a series of blind tests and blind test workshops, and I'll talk a little bit more about those a bit later on. We've also run some pilot projects and industrial secondments, really trying to get people together the codes that are developed into practice. And then also outreach activities to get young people and other people in the wider community excited about the work we do in computational modelling. The website is the place to go, hopefully, for most of this all of this information. We try to keep it up to date. Please do have a look there, sign up through there to the repository, to the network, and find out about events that are coming along. So the data repository is where we are saving or have a repository for data on benchmark test cases. So our plan is to have a series of benchmark tests that can be used. We have enough information there so you can set up the case. You've got the data for the result, whether it's an experiment or other numerical or theoretical model data. It can be accessed and downloaded freely from anyone just going to the website. And then you can use that as a benchmark to test your code and to compare the performance of a code or a developing code against other codes. We'd really like to extend this database of benchmark tests, and so we're trying to do that with our team and with the wider community. So if you've got ideas and suggestions for things that you'd like to see on there, then we're very open to those, and please do let us know. We also have a code repository in the GitHub, and that's also accessible through the website. You need to register to that, you need to join up because it's a private repository, but you can sign up through the form on the contact page, and anyone who'd like to can access that. And the advantage of that is that you can access the code that's being developed. So we have some code which can be downloaded and used, but what we'd really like to do is to have people using that repository environment to contribute their developments as well, so that we can together sort of expand the range of codes that are usable and supported through this code repository. Okay, so please, if you haven't already, very welcome to have a look at the website and see what we do there. I'd just like to talk now about some of the applications of the computational models we're developing and the interests of the team within the CCP WSI. And starting with Plymouth, and a lot of the work we do, our computational fluid dynamics modeling in wave structure interaction is strongly linked to the hydrodynamics work we do within our coast laboratory and our physical modeling there. So we have a very nice coast lab. We have a couple of wave basins and some flumes. We do lots of experiments, and this is our large ocean basin. And that's, well, it's like a swimming pool, really. It's 35 meters long and 15.5 meters wide, full depth of 3 meters, has individually controlled wave paddles, so we can generate any sort of complex waveform. It also has a current generation system, and just now we have investment in a wind generation system as well that will go over the waves, which will enable us to do all sorts of further exciting and complex experiments. And we're particularly interested in floating offshore wind and the combined loading there. So what sort of experiments have we done up to now? What sort of interest do we have? Coastal engineering and offshore and ocean engineering generally, but particularly interested in offshore renewable energy. We've done quite a bit of work on looking at new concepts and extremes for wave energy. This bag structure is a flexible wave energy device that we've investigated, a new concept. And this picture here is a floating tidal turbine. Well, the turbine is represented by a porous disc there, but that study was to look at the floating tidal. We've also done experiments to look at array interaction and moorings, interconnected moorings, and how that affects the array. This is another array study, also for wave energy. And then impacts and extremes, so impacts on wave energy devices, breaking wave interactions. And then here's a photograph from a project we did or my colleague Alison Raby did, looking at the extreme waves breaking over rock lighthouses. And in this project, we had CFD, we had structural modeling of the stone block structure, and we also had monitoring of the structures themselves. So the lighthouses themselves are also monitored. So a really interesting project with lab scale computational modeling and field monitoring as well. From Plymouth, we are running the Supergen in offshore renewable energy. And this is just a slide to show our research landscape, but there's lots of information there as well about the sorts of applications that we need these numerical tools to be applied for. So that was a slide on our physical modelling, and this slide shows some of the CFD simulations of some of those experiments that you'll recognise there as well. And these include floating or fixed structures in waves, also breaking waves, and some sediment dynamics work as well. The team at Manchester, Lee Margetts and his colleagues, he's looking at complex structural mechanics models, and he's done developing work with ParaFEM to create constitutive materials for different types of structure, complex structure. So this is an example with I think it's a diseased bone, but could also be applied to looking at a damaged structure, steel structure, for example. And he's developed this framework which couples together ParaFEM, the structural part, with OpenFOAM for the fluids part. Sorry, my light's gone off. Okay, and then we've got at MMU, Manchester Metropolitan University, there's research there going on to look at extreme loading of floating offshore wind turbines. So this is the collaborative project, and this is a really interesting test case for any sort of coupling of numerical models, because it includes the aeroelastic interaction, the hydrodynamics, the mooring, and also the interaction with the seabed. And here's a movie showing some of the work that's been done at City University, combining together their Quali FEM, which is a finite element method, together with OpenFOAM. And you can see there's a floating semi-sub structure there, moored to the seabed, with also the turbine interaction with the air. And at Newcastle University, they're interested in developing the what happens below the ground. So if we have a monopile wind turbine structure, so not floating this time, we're also interested in the wave interaction with the monopile. But what happens there, and the vibrations that are fed through the monopile, will also have a significant effect on the foundation and the soil structure interaction under the ground. So coupling together the structural response with the soil structure interaction and the fluid loading is interest there. And then thinking about the soil and how that moves on a much finer scale, if it's a non-cohesive, or if it's a particulate soil, or if it's some kind of sumping behaviour, then at University of Glasgow, then Tom Shire is working on discrete element modelling. So a sort of particle scale, which has been used to look at various processes and coupled with CFD. In geotechnics, the erosion and scour around monopiles, for example, and avalanches, and so on. So a wide range of interests in development of numerical models, and also applications that can be used for. But in all cases, then those numerical models need to be run in an efficient way, so that they can be integrated into the design process, ideally. And so that means we need to think about parallelization, or how to make them more efficient, how to run them efficiently, And then if we have different types of code dealing with different domains or different regions of the problem, then we need to think about how they couple together, and of course how that coupling can be parallelized as well. We're very lucky within the CCP that we have some contributions from SDFC, the experts there who are have some dedicated time to put into this and to help with it. So Stephen Longshaw is leading on the coupling side and developing a coupling framework using the MUI multi-scale universal interface library to couple codes together, and he's been working with OpenFOAM and ParaFem recently, but the plan is to sort of extend that work out more broadly so that we can develop a coupled framework. You know, eventually that various different codes or numerical models could be coupled into. Then Xiaohu Zhu is developing working on the parallelization and optimization of these codes, and working on high performance computers like Archer, for example, and developing that work using some of the same coupled codes and working the coupled codes together into and looking at the best way to develop that dynamic load balancing in order to make them run more efficiently. Okay, and there are some examples of these codes available already within the CCP code repository. This dynamic load balancing example that Xiaohu has developed is an example of parallel optimization, and then there's also some multi-region zonal CFT methods that are available there through the repository, and we'd like to see that repository grow over this period of the CCP and to have more coupled codes in there that are available and contributed from the community. I just have a couple of slides on the blind test series that we've run. So far we've run 3 blind test series, and the idea for these is that we have an experiment that we define well enough that anyone can set it up within their numerical model. We invite them to do that without releasing the data from the experiment itself, and then we compare the simulations from the different codes and compare those with the experiment, and it gives us an idea of, you know, the range of applicability of different codes and the variability in how they can be applied, and the sort of the things that they all agree on well and the things that aren't so well agreed. And we've sort of done these blind test examples with increasing complexity from a fixed structure in waves to a floating structure and then a more complex floating structure, and we've run those over the last couple of years. We've had a large number of people from across the computational community, nationally and internationally, who have taken part in those, and those have been presented at conferences at ISOP and UTEC, and also published in special issue journals as well. And the information on all of those is available on our website again. There's some very interesting findings on how the variability of even similar codes is evident there. The difficulty in setting up this type of study to make sure it's very well defined and that we can do a meaningful comparison. And it's also useful to define the test cases so that they can be used to differentiate between the different models, or the physics embedded in different numerical models. So there's some publications linked in there, and that's all findable from the website as well. We're planning our next blind test and some other upcoming events that I just wanted to mention quickly now. So the next blind test we run, we haven't finalized what that's going to be yet. We'll be very interested for suggestions or requests to come forward, so please do feed those in. We have the Code Developers Workshop we ran in April, that the presentations, information on that's available on our website if you're interested in that. We have a special session or showcase session for our CCP at ISOP this year, coming up very soon. And then just a heads up about 3 events that we're planning in the next year or so. We've got quite a bit of activity we want to do around coupling, to talk to people about coupling, to share some of the work we've done and develop our coupling libraries further. First of all, we'll have a training event in October. That's the first thing coming up. Then we'll be running a Code Developers Workshop and inviting people to contribute to that in March 2022. And then that will be followed later in 2022 with a hackathon, where we want to get people together who are interested in working together on developing some code and making some advances in the coupling. So that will also be coming up, and be very pleased to have any input from anyone here. If you'd like to get involved, then please do get in touch with us through the website. And there it is again. Thank you very much. I'll be happy to take some questions.
Great, thanks very much, Professor Greaves. That was a very nice talk. The experimental facilities you have in Plymouth are very impressive. Your coast lab, I imagine. I can only imagine the expense of keeping something like that going. Never mind setting it up in the first place, but it's very impressive. So if people have any questions or comments, feel free to put them in the Q&A. Or if you have suggestions for blind tests or any of the other questions that came up. So I'll read out some of these questions, and I've plenty of questions myself. So lots of people thanking you for the nice talk, and commenting on how impressive the Coast Lab is. Does the group work on air entrainment by waves, or are you working on air entrainment by waves?
We have done we had a project called Froth actually a few years ago, where we did some experiments looking at wave structure interaction with broken waves and air entrainment. So we did some work and some very nice experiments looking at wave breaking onto a vertical wall and air entrapment, and the different types of wave impact and wave breaking you can get. And then also how the forces on the wall will change as if the wave is already broken, is what I mean. So the compressibility effect in the broken wave. We also did some work with wave impact, dropping a heavily instrumented block into the center of the large wave tank, with pure water, and then also with aerated water. That work has been written up and published, so if anyone's interested in that particularly, I can send some information on that.
Great, perfect. So in the Q&A you can vote up questions and comments. So the top one at the moment is the Coast Lab is insane. So I think that's a comment rather than a question. Let me see. Lionel asks, is the CCP WSI consortium open to add new participants?
Yes, absolutely. I mean, it's a sort of networking consortium, so we're looking to grow the network all the time. So you're very, very welcome to join the network, yes, and take part in the activities.
Great. Richard asks, are there any comparison tests with SOFWA, so simulator for wind farm applications?
Okay, I'm not familiar with that. I'm assuming that might be something which deals with the whole of the wind farm.
Possibly, I'm not sure. So Richard, feel free to follow up with that a comment, and I can come back to it. Do you have any tests planned for flying and swimming at the intersection of water and air? I presume you mean, Chandon, maybe for vessels, I suppose, as opposed to humans, maybe.
Yeah, that's an interesting one. We have tests planned for floating offshore wind turbines,
Okay.
We have tests planned for some very interesting new wave energy device concepts with very flexible structures and structures that are containing air as well. So flexible membrane structures with internal air under pressure. So that's quite an interesting one. I don't think we've got anything actually flying or physically swimming, although
Sure.
I should say that we also have teams doing sort of autonomous marine system development, so they sometimes swim around in the Coast Lab.
Okay, great. I have a couple of questions as well. There's one of our sponsors is iForm. We're a research center here in Ireland that I'm actually involved in on advanced manufacturing, so particularly 3D printing. And it's a similar kind of idea, I think, to CCP. It's funding structure, many institutes involved. So do you have any comments on the challenges with coordinating such a large consortium with so many different universities, and us academics like to be somewhat independent in our own research direction? So it's hard to herd the cats at times. So do you have any comments on that?
Well, yeah, I suppose you know, some of these types of structures, the network structures, that, you know, there's not a huge amount of funding that goes with them. So you know, it's more about working with the community and running events and things and getting people involved in those events, and then leading on to further funding and project opportunities. I think, you know, with these things where you're you know, where you're sort of trying to encourage people to engage, then it's about making sure that we are doing things that are relevant and that people can see a benefit to. I think also, you know, making sure that everyone sees their role in it is important.
Sure. No, that's useful. So the code, just to clarify, the code is essentially all open source, is it, through your repository, or once it's been published you make it a repository, or how does it work?
Yes, well, that's the sort of the code. I mean, we've got a number of different codes, sure, really, and it's not like it's not in some of the CCPs then there is a single code that's being managed and maintained for the community. This one's a little bit different, so we have a number of codes that can be downloaded from the repository and used, and we're hoping that others just use that as a sort of development framework and can contribute their elements. But I think the coupling framework that we're developing now, this multi-scale universal interface type coupling system, we hope will be useful to then sort of couple in many different types of numerical model. So we're hoping to see that grow with more contributions and more examples of different codes coupled together.
Great. I know, I'm not sure if you're familiar with, there's the precise coupling software as well. I know, is it Jeremy's giving a training on Friday, so I'm not sure if you're familiar with that, but there might be some things you could build on there, or even include it in some way in your coupling framework. But yeah, very nice. And maybe one last question from myself. And for the blind tests, they're always really nice to see, particularly when you don't not releasing the answer in advance. And so I think I saw that there was maybe multiple groups using, say, the same software. So many groups may have used OpenFOAM. I'm interested to know how much of a variance was there between the different predictions, even when people use the same software?
Well, yeah, there was some surprising differences, even with people using the same software. And of course, when you're using something like OpenFOAM, you're probably not using exactly the same software, because you'll be doing a different setup or different libraries or different ways of doing the inlet boundary or whatever. And so I don't think we had any examples of people who were using exactly the same software, but there were a number of different examples of using OpenFOAM. Generally, what we saw is that the different types of code fell into different buckets. So all of the OpenFOAM or RANS type solvers were giving similar results, and perhaps a bit different from fully nonlinear potential theory, and then from other types of boundary element code or particle code. But yeah, so that they tended to fall within the different physics that's behind each of those models. But I think it certainly is still surprising, the variability that you get with a single code. And of course, although the first set of blind tests that we did, we hadn't specified so clearly, you know, we hadn't asked everyone to make sure they'd done a grid convergence test, first of all, for example. So that obviously makes a big difference. Also, the other thing that we did in the most recent blind test was to make sure that we'd released the wave only data, and really tried to encourage everybody to make sure that the wave only data was as close as it could be to the experiment data before embarking on the wave structure interaction case, because, you know, if the wave only case is out, then there's no chance you're going to get the wave structure interaction case right. So yeah, things like that, which always seem obvious in hindsight, but were very important to get right.
Sure, I can imagine it's been a learning experience, I guess. Fantastic. So thank you very much for the talk again. It was very interesting, and it was very impressive to see the breadth of software and hardware. So that's great. I'll bring this session to a close. And then for everyone else, I think it's at 12:30, so in 8 minutes, the final technical sessions will start. So thanks again, Professor Greaves. Thank
you very much. It's a real pleasure. Thank you.
Okay. All the best. Bye-bye.
Thanks. Bye-bye.